Hey everyone, welcome back to the channel. Today we're diving into the fascinating world of artificial intelligence. Specifically, we're going to break down different types of neural networks. Think of them as the brains behind how AI actually learns and processes information. We'll be breaking down the differences between 6 types of neural networks: probabilistic neural networks, feedforward neural networks, hop-field neural networks, recurrent neural networks, convolutional neural networks, and multilayer perceptrons. We're talking about what makes each one unique, how they work, and what they're best used for. So, let's get started. First up, we have probabilistic neural networks, or PNNs. Now, if you're thinking probability, you're on the right track. PNNs are all about using probability theory to classify data. Imagine you're trying to train an AI to differentiate between pictures of cats and dogs. A PNN would analyze a bunch of cat and dog images, learning the probability of certain features appearing in each category. For example, it might learn that a pointed ear has a higher probability of belonging to a cat, while a floppy ear is more likely to be found on a dog. Then, when you feed it a new image, it uses these learned probabilities to make the best guess about whether it's looking at a cat or a dog. What's really cool about PNNs is that they're generally faster to train than some other networks. They're like the quick learners of the neural network world. Plus, they can handle situations where you might have some missing data points. Think about it like this. Even if the AI only sees part of the animal in a picture because something is blocking it, the PNN can still make an educated guess based on the features it can see and the probabilities it's learned. Of course, like any technology, PNNs have their limitations. They can be a bit more sensitive to the amount of training data you give them. A smaller dataset might not give them enough to work with to make accurate predictions. But overall, PNNs are a powerful tool for classification tasks, especially when you need something that's quick and can handle a bit of uncertainty. Next up are feedforward neural networks, also known as FNNs. Now, FNNs are like the foundation of neural networks. They're the most basic type. Imagine information flowing through the network in one direction, like a one-way street. You input data at one end, it travels through the layers of the network, and then you get an output at the other end. No looping back, no complicated pathways, just a straight shot through. This makes FNNs super useful for tasks where you need a quick prediction based on a set of inputs. Think about predicting stock prices, for example. You feed the FNN historical stock data, and it spits out a prediction for the future based on the patterns it's learned. Now, within an FNN you have different layers: an input layer, one or more hidden layers, and an output layer. The input layer is where you feed the data in, and the output layer is where you get your results. But the real magic happens in those hidden layers. Each connection between the nodes in these layers has a weight associated with it, kind of like assigning importance to different pieces of information. During training, the FNN adjusts these weights based on the data it sees, trying to minimize errors in its predictions. Over time, it gets better and better at making accurate predictions. Now, while FNNs are great for simple tasks, they do have their limitations. They don't have any memory of past inputs, so they treat each input as a brand new piece of information. This means they're not the best choice for tasks where the order of the data matters, like natural language processing or analyzing time series data. For those types of tasks, you'd want to look at something like a recurrent neural network, but we'll get to that in a bit. Let's talk about hop-field neural networks, or HNNs. Now, unlike the one-way street of FNNs, HNNs have connections that loop back on themselves, forming what we call a recurrent network. Think of it like having a conversation with someone. You remember what was said earlier in the conversation, and it influences how you respond later on. HNNs kind of work the same way. They have a memory, making them great for tasks where the order of information matters. One of the key features of HNNs is that they use binary threshold nodes. This means that each node can only be in one of two states, kind of like a light switch that's either on or off. This might seem limiting, but it actually makes them really efficient at certain tasks, like pattern recognition and associative memory. Imagine you show an HNN a few incomplete patterns. Because of its recurrent nature, it can actually fill in the missing pieces based on the patterns it's learned before, almost like it's recalling a memory. This ability to remember and recall patterns makes HNNs particularly well suited for tasks like image restoration or even optimization problems, where you're trying to find the best solution among many possibilities. However, HNNs do have some limitations. They can be tricky to train, and their performance can be sensitive to the initial conditions you set them up with. Plus, they're not as good at handling large datasets or complex patterns as some other networks. But despite these limitations, HNNs offer a unique approach to processing information, especially when memory and pattern recognition are key. Now let's talk about recurrent neural networks, or RNNs, the masters of sequences. Remember how we talked about FNNs not being great with data where the order matters? Well, that's where RNNs shine. They're specifically designed to handle sequential data like time series, speech, and text. Think about it. When you're reading a sentence, you don't just process each word in isolation. You understand the meaning of the sentence based on the order of the words and how they relate to each other. RNNs work in a similar way. They have these things called loops that allow information to persist, creating a kind of internal memory. This means that the output of an RNN at any given time step is not only influenced by the current input, but also by the previous inputs in the sequence. It's like the RNN has a short-term memory of what it's seen before, and it uses that memory to understand the context of the current input. This makes RNNs incredibly powerful for tasks like natural language processing, where you might be trying to translate languages, generate text, or understand the sentiment of a piece of writing. They're also used in speech recognition, where the order of the sound waves is crucial for understanding what's being said. Now, RNNs can be a bit more complex to train than FNNs, but the results are often worth it. They can capture complex dependencies in sequential data, making them ideal for tasks where context and order are crucial. Let's dive into convolutional neural networks, or CNNs, the visionaries of the neural network world. If you've ever used facial recognition on your phone or seen those cool apps that can identify plants from a picture, you've witnessed the power of CNNs in action. They're specifically designed to process data that has a grid-like structure, like images and videos. Think about an image. It's essentially a grid of pixels, each with its own color value. CNNs are designed to extract features from these grids like edges, corners, and shapes. They do this through a special type of layer called a convolutional layer. Imagine sliding a small window over the image, looking for specific patterns. That's kind of what a convolutional layer does. It has these filters that scan the image, looking for specific features. Each filter is like a detective, trained to recognize a particular pattern. As the filters move across the image, they create feature maps that highlight where these patterns are found. These feature maps are then passed on to other layers in the network for further processing. What makes CNN so powerful for image recognition is that they're translation invariant. This means that it doesn't matter where in the image a feature appears, the CNN will still be able to recognize it. Whether a cat is in the top left corner or the bottom right corner of an image, the CNN will still be able to identify it as a cat. This ability to extract features and recognize patterns regardless of their location makes CNNs incredibly powerful for a wide range of tasks beyond just image recognition. They're used in self-driving cars to detect objects on the road, in medical imaging to identify tumors, and even in gaming to create more realistic graphics. Finally, let's talk about multilayer perceptrons, or MLPs. These are like the sophisticated older siblings of FNNs. Remember how FNNs have those input, hidden, and output layers? Well, MLPs take it up a notch by having multiple hidden layers. This allows them to learn more complex relationships in the data. Think about it like this. Each hidden layer can learn a different level of abstraction. The first layer might learn simple features, the next layer might combine those features to learn more complex patterns, and so on. By the time the data reaches the output layer, the MLP has extracted a rich representation of the input. This makes MLPs incredibly versatile. They can be used for a wide range of tasks, including classification, regression, and even pattern recognition. You'll find them used in everything from spam filtering to handwriting recognition. Now, training MLPs can be a bit more computationally intensive than training simpler networks, but their ability to learn complex relationships in data often makes it worth the effort. They're the go-to choice when you need a powerful network that can handle a variety of tasks. One thing to keep in mind with MLPs is that they're still feed-forward networks. This means that information flows in one direction only. They don't have any memory of past inputs, so they're not the best choice for tasks where the order of the data matters. But for many other tasks, MLPs are a powerful and versatile tool. And there you have it, folks. A quick rundown of the differences between PNN, FNN, HNN, RN, CNN, and MLP in AI. We've covered a lot of ground today, from probability-based classification to image recognition and everything in between. If you found this video helpful, make sure to give it a thumbs up and subscribe for more tech content. And be sure to let me know in the comments which neural network you found the most interesting. Thanks for watching, and I'll see you in the next one.